Hi, I'm Leon Starr, and this is lesson 220 of my course, How to Specify Software in Complex Safety Critical Systems. In lesson 210, Platform Independent Classification, we saw how we could classify the entities in our system's world and then model their data using tables. It's this underlying table formalism that makes our classes executable. So here, in executable classes, we'll take a closer look at the operations or actions that let us manipulate these tables. But first, why tables instead of something else? There are all kinds of executable data structures that we could use to formally represent our data. When we implement, we typically need a wide variety of data structures and their associated operations to achieve the desired efficiency. We optimize for a certain type of lookup, or maybe memory utilization, or maybe we're just trying to make the best use of the idioms of a given language or framework. But we're specifying, not implementing, so our goals are different. We'll leave it to the programmer, code generator, or AI to select the appropriate data structure. And there are multiple reasons why this is a good idea. For one, we simplify our specification by focusing on the essential data and relationships and not getting caught up in their implementation. So, getting back to tables. Our use of tables represents an application of relational theory. And when I say relational theory, I'm not talking about relational databases. Those are just another implementation platform. Relational theory, on the other hand, is simply a branch of mathematics. This branch is an extension of set theory, functions, and predicate logic that expresses relationships among data. So our modeling platform is, in fact, a mathematical platform. Tables that cover the rules covered later in this video are a way of accessing the underlying math without having to be mathematicians ourselves. You can dig deeper if you like, but there's no need if you just want to create a formal specification. So we can get the benefits of the logic without having to read and write expressions with Greek letters and all those funny upside-down symbols. So if we aren't specifying implementation, do we care about efficiency at all? Yes, but there are two kinds of efficiencies that concern us. The first is efficiency of the specification itself. In other words, we want our specification to be no bigger than it needs to be. So, given two models of the same problem, we tend to choose the less complex model that specifies the same data, rules, and behavior. Or given two models where one is a rigid statement of today's known requirements, while another can readily adapt to imminent changes in those requirements, we probably want the more flexible, more configurable specification. The second kind of efficiency pertains to the target platform. For example, a given platform may need to make implementation choices based on maximum populations of certain classes. A different platform might care about which class populations are static throughout runtime. To keep our models platform independent, we can provide this information by marking up our models on a platform-specific layer. You can think of it like a transparent sheet of performance cues or implementation cues overlaid on the models. That's just a visualization, but we use markup files for the same purpose. Thus, a given platform or deployment can take into account both the single set of platform-independent models and whichever set of markup files is relevant. Marking is a whole topic of its own, worthy of at least one of its own videos. Now we need to lay down some simple rules about how our class tables are defined. Left unchecked, tables can turn into wild spreadsheets that destroy the integrity of our data and make execution unnecessarily complicated and unsafe. We're specifying safety critical systems, so we certainly don't want that. Fortunately, the underlying relational theory gives us a handful of well-researched rules that we'll be using throughout this course to keep our tables and models under control. And this theory will ensure that when we specify actions on tables, we'll be able to make simplifying assumptions that streamline our logic, making it more reliable and easier to validate. The central idea is that a row-column intersection of a table, or cell as we'll call it, always contains one fact, not zero facts and not multiple facts. Let's explore this idea with a class that defines different designs or models of aircraft. Here we see instances of Boeing 747, AB310, and MD-80. Note that each aircraft model has its own name. Each specifies a maximum range and a wingspan. Surely there are many other attributes and components we could consider, but for our purposes we'll stick to just these attributes. Now if we look at max range, for example, we see a single fact specified. It says that a Boeing 747 has a maximum range of 13,570 kilometers. In other words, there is a single value representing a single fact in the max range column for a Boeing 747. The name column, however, is not so simple. Let's say that we have selected the aircraft model with a wingspan of 64.4 meters, and in our example there's only one such instance, and now we ask the table, what is the name of that aircraft? Or rather, what's the name of that aircraft model? We get a simple answer, Boeing 747. And sure, you could argue that this is a single fact. It's the name, right? Or is it? If it is just a name, you can't ask who the manufacturer of that aircraft is. Even though you see the name right there, remember that we plan to treat all instances the same. The table is actually embedding two separate fields in the name column and not doing it very consistently either. If we select AB310, for example, we would have to know somehow that AB corresponds to Airbus. The model as it stands does not provide that information. And if we selected MD80, we might know that MD stands for McDonnell Douglas. But this aircraft model is in fact owned by Boeing these days. Now, if we don't ever care about the manufacturer and we just think of the name as a name, this is okay. Then it's just one fact, the name of the model and nothing more. So you cannot infer the manufacturer. But if our requirements tell us that we do need to answer that question, we need to revise our class. Let's split out the manufacturer from the name and add the appropriate attribute to our class. We then update our table and can see that each cell now has a single fact. And while we're at it, we can remove Boeing from the 747 name and even remove AB from AB310 since the new attribute has already extracted that information for us. We may, on the other hand, want to keep MD in the MD80 name since that really doesn't have anything to do with the current manufacturer, and that's what everyone calls it. But unlike before, we don't need to parse the name and play games to infer the true manufacturer. Yay! Now we aren't treating any of the instances specially, and the logic we use to process the table is less error-prone. I want to point out that there is no universally correct aircraft model class pattern. Ours is a consequence of our unique system requirements and our modeling decisions. The number of facts in a cell shall be 1. Thou countest not to 2, and 0 is right out. Let's add a couple more attributes to our example table and attempt to put some non-facts in a few of the cells. The trouble arises from Model 28B by ASW, which is in fact a glider. This distinction causes some trouble in our table. First, we note that there is a 0 in the engine quantity column. That's all right, 0 is a perfectly legitimate value, but it does hint that something could be special about this instance, so it does get our attention. It's the not applicables that cause trouble. Not applicable means that there's no relevant fact for this particular instance. The engine inspection interval is not relevant because there are no engines. And actually, the fact that the value 0 has an effect on the meaning in a different column causes us other problems that we'll discuss in a future video. Also, the maximum range is not applicable since it is computed based on fuel consumption, among other factors, and fuel consumption is also irrelevant to a glider. If you haven't guessed it already, what these not applicables are telling us is that our classification is broken. Not all instances are really the same, certainly in terms of their characteristics, and that breaks our class definition. Gliders are a special case. So we need to adjust our classification somehow. I recommend pausing the video and thinking about how you would refactor the class to eliminate the need for the empty cells. One approach is to think in terms of 3 separate classes. The one on the top is the general case applicable to any aircraft model, while the other 2 classes, powered and unpowered aircraft, handle the special cases. This is a technique called generalization specialization, which we'll cover in a separate video. Focus though on what we're doing. Rather than hiding the special case of a glider, we've exposed it. When we specify, we want to expose subtle differences. This is often the opposite of the programming instinct, where we often pack special cases into a single structure for efficiency. And that's fine for programming, but our job is to bring attention to the nuances of our system. Now, you might be a little uncomfortable with the glider, unpowered aircraft model table down there on the lower right. It's just sitting there with no special attributes. That's actually okay. It's just telling us that for unpowered aircraft, there are no special attributes. It's not an implementation, it's a specification. That said, lonely tables like this have a way of expanding once they've been exposed. I mean, your discomfort forces the question, Are there any such attributes peculiar to unpowered aircraft? How about these two? Assuming those are legit, our reclassification forced us to think more deeply about our system. It may have forced us to go back to the subject matter experts for clarification. That's all part of the magic of forcing our data into a formalism as we model, instead of just drawing class symbols. Here is another case with troublesome cell content. The first column is just the airport code, so no problem there. Now the second column might look suspiciously like two facts jammed together, but it's just a location expressed in GPS coordinates. Where's the aircraft right now? It's here. So it's really a single fact with some internal structure. This is okay as long as the data type and its supporting operations are well defined. I'll cover the definition of types in a future video. But the third column is problematic. It has multiple values in one of the cells since the Atlanta airport has two control towers. This sort of a thing where a set of multiple facts are clumped together breaks our table rule, so we need to refactor a bit. We probably want to abstract the control tower class and then add a referential attribute for the associated airport. I'll be introducing referential attributes in Lesson 230. In addition to the one fact per cell rule, we place no significance on row or column order in our tables. That's because deep down, we're thinking in terms of sets of attributes, types, and instances which have no implicit ordering in the underlying relational theory. So if we shuffle the row or column order, the table is still specifying the same exact information. There are times, though, when we'll need to specify order, such as the sequence in which aircraft are queued for takeoff. In such cases, we have a way to model the order explicitly using a couple different types of relationships, and we'll focus on those techniques in a future video. Now that we've established our table rules, we can talk about how we think of our class model as being executable. What do we mean by executable data? Data itself doesn't actually do anything. But when we specify computations, we'll need a way to manipulate and access the data defined in our class model. Each action that can be performed on a class is defined in terms of one or more table operations. If we want to specify the creation of a new instance of a class, for example, we can imagine a table operation that inserts a new row with the value supplied for each attribute of the class. Let's say that a Qantas flight enters our airspace. We'll need to create a new instance of aircraft by inserting a new row in our class table. Similarly, if a flight leaves our airspace, we'll need a delete action. The corresponding table operation removes a row from the table. We frequently need to select a set of instances based on some criteria. Let's say we want all instances of aircraft flying below 5,000 meters faster than 240 kilometers an hour. The restrict table operation takes a predicate and returns all rows where the predicate evaluates as true. Here we end up selecting two instances. But maybe we only want the IDs of those aircraft. The project operation chooses values from a set of 0 or more attribute columns. So we specify the ID attribute, which yields a set of two values. The restrict and project operations are typically specified together. We also need a way to read and write our attribute values. Typically, we will first specify an instance set and then read or update the relevant attributes. Okay, time to wrap up. Key points in this video. There are just a couple of rules that we follow when structuring our class tables. Rule 1 is that a row-column intersection, or a cell, must contain exactly one fact. This means that not applicables and nulls are not allowed. You can't embed extra facts inside the content of a cell, and you can't just jam an unending series of values in a cell. That said, you can define a value to be as complex a structure as you like, but you'll need to define a type and a set of operations for processing that value. Typically, we only do this for values with well-defined structure and supported operations, like say a GPS location, timestamp, vector, or maybe some kind of image transform. These rules help us tackle complexity, keep our data consistent, eliminate redundancy, and avoid a whole host of well-researched data integrity problems, and keeps our model logic as simple and powerful as possible. Adherence to the rules sets us up to specify actions with a small set of simple table operations. We can read and write attribute values, we can create and delete instances, and we can grab a subset of instances and their attributes based on any criteria we specify. There's a lot more to say about both good and bad classification, and we'll get into that in future videos. But as you may have guessed, most of the interesting rules, logic, edge cases that you need to specify involve multiple classes. So for a given class, how can we specify rules about what instances can be related to other instances and when? More importantly, what relationships detected in the real world would tell us that something nonsensical or dangerous is happening? We'll begin our journey into rule specification by way of executable relationships in video 230, coming up next.